Okay, so the diagonal rule. It's all fun and nice for helping you to get your electron configurations. By the way, don't forget these electron configurations are telling you the energy states of the electrons in the atom. And that's going to become extremely important when we talk about bonding coming up very soon. So we need to know these configurations, and you'll see why as we start using them. But you need to get them. So diagonal rule is a great way to do it. But as you saw in some of the examples we did and on the quiz and all that, the bigger ones can get pretty tedious. If you're doing like lead with 82 electrons, that's a lot of 1s2, 2s2s all the way out to wherever it ends up. So it's nice to have a shorter way of doing it yet. Now, the periodic table is going to give us a shorter way of doing it. I just so happen to have one right here, a blank copy of the periodic table. Now, if you look at the periodic table, hydrogen's right here, 1s1. Helium 1s2 over here. Now we're done with level 1, so follow the diagonal rule. Lithium 2s1. 1s1, 2s1. Okay, now 2s2, 2p, 1, 2, 3, 4, 5, 6. And now after 2p6, which right here is your noble gas, remember, 3s1. So you'll notice hydrogen ended up as 1s1, lithium here ended up as 2s1, sodium right here ends up as 3s1. Potassium right down here, guess what that's going to be? It's going to be 4s1, of course, right? So we figure that out without even going through the diagonal rule. We could 3s1, 3s2, 3p, 1, 2, 3, 4, 5, 6, follow the diagonal arrow to 4s1 so it agrees. Next one down, 5s1, 6s1, 7s1 for francium down here. So that's not the whole configuration. You got to go through the whole works. But we already know francium is going to end up as 7s1. So it's a really good way to check your work if nothing else. You're going through doing your whole diagonal rule, all the configuration. You know it's going to stop at 7s1 because it's right here on the periodic table. Okay? Coming back up here. Now this was potassium, 4s1, 4s2 for calcium right here next to it. Now you go into these transition metals. You go back, now after 4s2, look at your diagonal rule. You go back to 3d1, 3d2, 3d3, over to 3d10 right here. You go back and fill the 3ds. And now you're back up to 4p1 over to 4p6. Notice the periodic table is following the diagonal rule. Okay? Or I guess another way to say it is the periodic table is the diagonal rule. It's just that when they first invented the periodic table, they didn't know that. They just knew the elements fell in these patterns. We now know why they fall in these patterns is because of the electron configurations. Now, notice though that we found S1s were always in this column. S2s are always in this column. Except helium, it's over here because it's a noble gas. It's weird because there's no 1p. If there was a 1p, there'd be elements up here. And helium would in fact be over here acting like the other S2s. Okay? But it's a full shell, so helium acts weird. It acts like a noble gas because it's a full shell. But other than that, all your S2s are right here. Okay? So, if I ask you, say, what this element right here, its configuration is, I'll put a dot there so you don't forget. Well, count down. 1, 2, 3, 4, 5. We're in level 5. It's 5s1, 5s2. So that element, its configuration is going to end with 5s2. Yeah, it'll go 1s2, 2s2, 2p6, blah, 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 blah. But we know it's going to end as 5s2. Okay? And that's pretty powerful, knowing at least where it's going to end. So, I'm going to erase that little dot so we don't get messed up. Notice I'm going to partition this off. This section right here is the S block. Everything in that section ends up with S something. S1, S2. Okay? Which level are you in? Well, whatever row you're in. Right here, you're in the first row, it's 1s1. Here you're in the second row, it's 2s1, 2s2. Third row, it's 3s, 4s, 5s, 6s, 7s. So francium down here is row 7, so it's 7s, and it's the first one, so it's 7s1. You go over here next door to radium, it's the second one over. So we're still in level 7, it's 7s, it's the second one, so it's 7s2. Okay, so that's your S block. What about the rest of it? Well, notice this was P1, P2, P3, and so on. This over here is the P block. Sounds like we're doing a prison movie here. So that's your P block. Now, I guess we got to leave helium out of that because it's weird, remember. So, we know this whole column is going to end up as P1. These are going to all end up as P2, P3, P4, P5, P6. Which energy level are you in? Same as before. This is all level 1. This is all level 2. The P's are filled out at the right level. This is level 3, level 4, 5, 6, 7. So if I ask you about this element right here, well, it's 1, 2, 3, 4, 5, 6, 7. It's a 7p, count over. 1, 2, 3, 4. So that element, which I guess is polonium, or no, I'm sorry, it's whatever weird one lies below polonium, is a 7p4. Okay? Let me erase that dot. And let's go to this element right here. Okay, we're in the P block. 1, 2, 3, 4, so it's 4p. 4p1, 4p2. That element ends as 4p2. Okay? So you can get your configuration, at least what it ends with, right there from the periodic table. What about these guys in the middle? Well, that was D1, D2, D3, and so on, so that's your D block. Okay? Now, don't forget the D's are filled a level behind. So right here, count down, level 1, 2, 3, 4. That was 4s1, 4s2. This element, which is scandium, we're in the D's, so you're a level behind. It goes back to 3D. So that's 3D1, 3D2, 3D3, all the way over to zinc right here at 3D10. Okay, so don't forget your D's are one level behind. 4s2, 3D over to 10 right here. Now if you continue back up to 4p, 1, 2, 3, 4, 5, 6. The P's are back on the right level. So your D's are a level behind. If I want to do, say, this element right here, 1, 2, 3, 4, 5, 6s2, go back to 5d, 1, 2, 3. It's the third D over, so 5d3. Okay? So, finally, these guys down here, which luckily we won't have to worry too much about, but they exist, so whatever. That's the F block. There's 14 across there. I don't know if you ever counted these. This is a block of 2. This is a block of 6. The transition metals are a block of 10. The lanthanides and actinides are a block of 14. 2, 6, 10, 14. Sounds familiar, doesn't it? These are just your electrons that fit into the orbitals. So down here you have the F block, F1, F2, F3 over to F14. Now remember though, these guys are actually a C below from right here and right here. Okay, one dot for that, double dot for that. Oops, well, whatever, I'll make a line there too. But I just won't do that. So, from right here, you go down there, F1, F2, F3, F4, and so on. But now don't forget, F's are 2 levels behind. 1, 2, 3, 4, 5, 6s2. Now you go back to 4f, 1 through 14, and now back up to 5d. We're a level behind. 6s, 4f, 5d. Now we're back up to 6p, back on the right level. Okay? And if you scroll up to your diagonal roll, you can follow that. 6s goes to 4f, 5d, 6p. 6s goes to 4f, see below, to 5d, to 6p. Okay? The periodic table is the diagonal rule. Okay, so that's an important thing to realize. I guess I went down too far. Now, because of that, it gives us an easy way to kind of shorten up these electron configurations. The other day, for an example, we did tin, which was, let's see, 5p2 it ended up with. 1, 2, 3, 4, 5. So right here is tin, SN. Okay, so there's tin. We want to know its configuration. Well, we know 1, 2, 3, 4, 5, fifth one down, p block, second one over, so 5p2. So we could write out 1s2, 2s2, 2p6, blah, 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 the whole thing, but let's shorten it up. What really matters is that we're in energy level 5 here. All the rest is buried deeper inside the atom. Remember, nucleus is here. Level 1 is close to the nucleus, level 2 further out, level 3 further out still, and so on. So once you're out in this outer level here, those lower level electrons, they're buried deep inside the atom. Who cares? If I'm another atom, I want to come in and react with this, bond by sharing electrons or giving and taking electrons, it's these outer shell electrons I'm going to bond to, or what we call the valence shell electrons. So those are the ones I care about. So how you do this shorthand is you start with the beginning of the row it's in. Okay? It's right here is the beginning of the row. That is 1, 2, 3, 4, 5s. 1, 5s2. So we got 5s2. Then what? After 5s2, we go to this. D's are back a level, so 4d over to 10. And then keep counting. Keep losing my cursor. After 4d10, now you go into the p block. P's are back on the right level, level 5, p1, p2. So 5p2. And that's the electrons that really matter, is what it comes down to. But now, we can't just say that's the whole configuration, because what happened to 1s2, 2s2, 2p6, and all that? Well, what we do is we shorten it up by saying, okay, well, everything before this. Well, what elements before that? That noble gas right there. Okay? What noble gas is that? Helium, neon, argon, krypton, right? So we can basically say whatever krypton has, which is all the 1s2, 2s2, blah, 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 all the way up to right here. Whatever krypton has, and then plus this extra 5s2 over to what we did. So we show that whatever krypton has thing by writing it in brackets. Okay? And we call that a noble gas core. Okay? So this is a shortened electron configuration. I didn't have to write everything out from 1s. I could just say, all right, I know everything from 1s up to krypton. And now what really matters is starting over here, 5s2, 4d10, 5p2. Okay? So let's do one more. Let's do iron. 1, 2, 3. Iron is right here. Okay? So what noble gas comes before iron? This one right here, which is, let's see, helium, neon, argon, right? So it's the argon core. I'm going to scroll up so I can do this. Argon core. And then what? There's your argon. Begin with the row that iron starts in. 1, 2, 3, 4s2 right here. And then, continuing after 4s2, we go back to 3d, 1, 2, 3, 4, 5, 6. 3d6. And that's writing your electron configurations using noble gas cores. It's kind of a shorthand way of writing our shorthand. And it makes life a lot easier, especially if I gave you like an element way, way down here where you had 90 electrons, 100 electrons to work with. This makes life a lot shorter. All right? For tonight, I'm going to give you a few to try just writing out as electron cores, and then we'll go from there.